Hello. So thank you for coming to the last session of SAS. I'm very honored to share this session. So the invited talk will be given by Loris D'Antoni, and we will see how to analyze infinitely many programs at once. So we are very interested.
Oh, can you hear? Let's see. Yeah, I'm there. Awesome. Okay, everybody can hear me. Good. So now we can move beyond the catchy title. And so this talk is as the talk says, about verifying programs. And I assume many of you have seen this. You have a precondition, a program, and a postcondition. That's program verification of one program. Today we're going to verify many programs. So we're going to have, the idea is that we're going to have some inputs on which we want to run many possible programs, and we want to satisfy a postcondition. So in this case, what we want is that all of those programs satisfy the pre-post condition. Cool? The setting is good? And the important question is, why do you want to do this? And the whole story is Happing's PhD dissertation, which was a very successful PhD. He is now a scientist at AWS. So it was a good PhD because he found a job, which is the main goal in life, I guess. Well, one of the main goals, besides all the other fun stuff. And basically, the story of his PhD started as follows. And I'm going to tell you why it's a successful PhD story, because it kind of came, it's a good lesson today if you're a PhD student in the room, that sometimes what you're going to work on comes later on in your PhD. You actually don't know it to start when you start. So Happing was working on this problem. This was his first problem I gave him. Like, look, people write these programs for modifying strings. They're called encoders and decoders. And it feels kind of silly that whenever we write an encoder, like the program that takes a string in one format and turns it into another, we also have to write the decoder. Because once you encode the string, there is only one way to decode it. So can we synthesize the second program automatically? And Happing's insight was that instead of synthesizing these really big programs, you can focus on little bits of them, and you don't need to understand what this program does, but the idea was that we can reduce this big synthesis problem to small synthesis problem. And we were very happy, because at the time, there was this thing that came out, which was called syntax-guided synthesis, which was promising to be able to solve small synthesis problems. So if we knew to solve small synthesis problems, we could also solve big synthesis problems. And what is syntax-guided synthesis? Is a framework where you write a specification in some form of first-order logic, and you say, I want a program S that does a bunch of things. This program, you don't need to read it, is the specification of the max of two numbers. And you give a search space, which is a grammar of programs, and you say, I want you to find a program in this search space that satisfies the specification. And then the synthesizer will go and look for one such program. In this case, for example, if x greater than y, return x tells y, it's a valid implementation of max, therefore it's a valid solution. Here is another solution. It's just a weird syntactic rewrite of the same program. Okay? So there are tools out there called Cygos solvers that if you give the thing on the left, on a good day, they give you the thing on the right. Okay? And people have used Cygos for a lot of things. I'm not going to talk about those in this talk, but if you're curious, there is a lot of applications. Okay. Great. Happing was very excited. So he was basically taking things like this, these little lines, and encode them. I'm not going to tell you how, but he's going to encode them as synthesis problems. And then he was going to call a solver. And in this case, this is one possible solver. And he was getting good solutions like this one. You don't need to understand what that is, but it looks nice and small. And we like nice and small when we have to write programs. But sometimes he called a different solver, and he got a different solution. And this was CVC4, what he was given at the time. So that doesn't look like a small program. In fact, it's bigger than the program we start with. And you don't need to read it, because probably you can't also physically. But basically, this program says, if the input is the bit 1, the output is the bit 7. If the input is the bit 2, the output. And this is for an 8-bit bit vector. So correct, not great. OK. So program synthesis was unpredictable. Basically, you were in this situation where if we changed from the grammar representation we had before to a visual representation, you have a search space of programs, the grammar, and you have a set of valid solutions. And in this case, what we had is that there were two valid solutions, that they were both correct, but one was better than the other. And the point is that at the time, there was no way to say which one you prefer. A solver could give you either of these, and they were valid solutions. There was no way to say, I prefer one over the other. And so here I want to focus on Happing's face. So at the time, he was very happy. But then when this happened, he became very sad. And look what you can do these days with artificial intelligence, yesterday, in just 20 minutes, I could make happy look sad. And nobody had solved this problem. And so Happy was a little bit frustrated at the time because he was like, he wrote this paper and this tool kind of was throwing crazy solutions. And this is the kind of the point, that the lesson for PhD students that are sort of in your first year, this will happen, you will get stuck. But when you get stuck, you can either be sad, which is a valid answer, but also you can see this as an opportunity. Basically, we found something that the state of the art was failing at, and this was a great opportunity to actually work on something hard that people hadn't thought about. And this what I just showed you basically led to the whole line of work that I'm going to present in this talk. Okay? So basically, Cygos was not able to say, I prefer one program over the other, and Happy came up with this thing called QCygos, which is a very simple idea. I'm not going to show you how it is defined, but the idea is that it allows you to give preference over syntactic features of the program. So for example, there you could say, I want the program with the fewest if-then else's. Okay, so the first program had 0 if-then else's, the one synthesized by CBC4 had millions. So you want the one with the fewest. And so when you do that, then Happy had a very clever technique that basically could use existing Cygos solvers to solve this problem. And the technique basically will do the following. It will find a program, in this case, let's say this one, and then it will modify the search space to only accept programs that were better. Okay? It will come up with a new grammar that only accepts smaller programs, or programs with the fewest if-then else's. And now you can do this, and you can do this, and eventually you get the best program. Okay? That's the optimal solution. And here came the big problem. How do I show you that that solution is the best one? What I have to do is I have to produce a proof that all the programs in the red space are wrong. Okay? If I want to show to you that this solution is the best one, I need to show you that any program that is left is incorrect. And we wanted the proof of that, and instead what we were getting was timeouts, fail, non-terminate. So the solvers were just like going to start running forever and not find a solution because they were very good at finding solutions, but not at proving that one wasn't there. And now I think you get the connection. So basically, this is called unrealizability. So I have a specification. I have a grammar of programs. In this case, there is no program of this form that can compute the max of 2 numbers. And what we wanted was the answer unrealizable, which is a proof that there doesn't exist a program that satisfies the specification and lies in this search space. And this sounds like a verification problem. So that's why we want to verify infinitely many programs at once. So basically, just to rewrite it, what we want to have, and this is kind of where things get interesting, I want that for every program in the search space, I want to prove that there exists an input that falsifies the specification. Okay? S, though, here is a program, okay? Is not a first-order term. And the challenge here is that there may be infinitely many programs, and for each of them, the witness might be different. So to prove that each program is wrong, I might need to check it on a different inputs. Let's look at this with an example. So this is the example I gave you before. The specification here, again, you don't need to read it, but it says this computes the max of 2 numbers, x and y. And this is the search space. You can do x plus 1, x plus 2, x plus y plus 10, whatever. There is infinitely many programs. That's the important part. And I want to show that all of them are wrong. So let's look at possible inputs. So here I have 3 inputs. Input 0, 1, the max is 1. Input 1, 0, the max is 1. Input 0, 0, the max is 0. And there is 3 possible programs, x, y, 1. So what's interesting here is that if I take any of these programs, each of them satisfies 2 of the examples and fails the other. So again, the input falsifying the example is different for each of them. And in this case, things are actually pretty good, because you can only come up with finitely many inputs for which you can get programs that differ. But I will show you, if we have time at the end, there are cases where you need infinitely many possible witnesses for infinitely many possible programs. Okay? So 2 challenges. Potentially, we need to reason about infinitely many programs. Potentially, we need to reason about infinitely many falsifying inputs. And this brings us to kind of the first slide we saw. So you have an infinite set of programs, or a large set of programs, some set of programs, and you want to prove and assert something that says on every possible program input, each of those programs produces a wrong output. Okay? So now we are in familiar territory. And as I said, you want to prove this for every S. OK. Now that I showed you why we care about solving this verification problem, and I'm going to show you more examples at the end, I'm going to show you what we did in this work. So having led the first two efforts on this, and as I said, this is kind of story of a successful PhD, it started with something that had nothing to do with this, but again, like research kind of comes to you in weird angles. It led to this work that kind of, it did this very nice two works that I'm going to show you first. And then I'm going to show you the work from my current student, Jim-Woo Kim, that he then took this to really a whole new level beyond new applications. And so in particular, I'm going to first show you some techniques that are specific to Cygos. So we just saw this synthesis framework that we care about. And then I'm going to show you the first work that then moved these ideas to reasoning about arbitrary programs, like imperative programs. And then finally, I'm going to show you a work from this year where we have actually a logic, like Hoare logic, to reason about these infinitely many programs at once. OK, let's start with the first paper. So like all first papers on a topic, it's going to be very easy. And, but it's good. It's that we were proposing a new problem. We didn't know what we were doing. And so we came up with the easy solution, which is what you want to do. So you have a Cygos problem, so a synthesis problem with a specification and a grammar. And I'm going to restrict now that my specification only comes through examples. So I have, in this case, 4 examples. They kind of show is the max function. So the max of 0, 0 is 0, and so on. And what I want to show, what I'm going to do, I'm going to show you that we can build a normal verification problem, like a classic reachability problem, such that the assertion in the program always holds if and only if this problem is unrealizable, meaning this synthesis problem has no solution. The nice thing of doing this is that at the time, it wasn't obvious how to do it, but once we did it, we could use existing solvers to do so. OK, let's look at the idea. And the whole paper is in one slide. So, well, one plus a few more of why it doesn't work. So, OK, so what I'm going to do, I have my inputs. In this case, there is one input. I want to show that on the input 1, 0, I want to check whether there exists a program that can output 1. So in this case, I'm going to start with one example. And I'm going to put that example in 2 variables, x and y, x0 and y0. So now here comes the magic. And this is where things get interesting for people who work on verification. I'm going to have a magic function called fstart that non-deterministically picks a program in my search space and runs it on x0 and y0. So this basically takes any program in the search space, one, non-deterministically, and runs it. And I'm going to show you in a second how to do that. And computes the output on x0, y0. And now all I need to do, if I can do that, I need to assert that that output is wrong. Is not, I wanted 1 is not 1. So if this assertion problem, if this assertion is always true, it means that no program in the search space satisfies this example. So I'm going to do it for one example now, OK? So how do I build a program that non-deterministically runs all the possible programs in my search space? Well, basically, I'm going to mimic the grammar that is given to me. So I have this grammar of the programs that I'm trying to run. I'm going to non-deterministically pick a production each time and run the corresponding program. So if I'm running the program 0, all I have to do is return 0. If I'm running the program x, I need to return the x component of my example. Things get a little bit more interesting when you do recursion for productions that build bigger programs. So I'm going to non-deterministically build 2 subprograms, run them, and combine the output. OK? So this is overly simplified, but this is really the idea in the paper. And I hope this is really nice, though, because it shows exactly what we showed at the beginning. I basically have a precondition, some set of examples I'm running. I have some sets of programs I'm building, and then I'm verifying an assertion. And the assertion here holds if and only if this is unrealizable. So in this case, this particular problem will be realizable because there is only one example. In particular, there is a program that on input 1, 0 returns 1, the program 1. So we need to put more examples. So this works. It can handle the case that we have infinitely many programs, but it cannot guarantee that we are falsifying, that different programs falsify different examples, because I've only given you one example. So here comes the tricky part, and I want you to pay close attention to the point in this slide because it's subtle, and is one of the key points that distinguishes the problem I'm talking about from many other verification questions. The program I built guarantees that on that example, so the assertion will fail, meaning I can get a program that actually outputs 1, if there exists a program that outputs 1 on this example. If I create a new problem with a different example, the assertion will fail if there exists a program that outputs 3 on those examples. But these two problems together don't mean that there exists a program that is correct on both examples, if both assertion fails. So what I need, basically, there might be different programs. So in this case, there is this issue that I need to synchronize my inputs. I haven't checked that there is a program that is correct on both examples. I've only checked that there is a program correct on one and the program correct on the other. So I cannot compose assertions in the usual way. So what we needed to do in this paper, and again, this is a crucial point that is going to kind of, we'll have to piggyback for the rest of the talk, to make sure that the program is not correct for the synthesis problem. It has to be wrong on one example, but we still need to feed all the examples at the same time. So in this case, we would basically execute simultaneously each program we sample non-deterministically. We need to execute it on all the examples. If you have 2 examples, you need to compute the 2 outputs kind of in parallel. And at the end, you check that one of the outputs is wrong. So in this case, this new problem I wrote will say this assertion fails if some program is correct on both examples. And dually, this program verification problem will be good, the assertion is true, if all the programs are wrong on at least one of the 2 examples. Okay? So this is one of the key new things. So from now on, basically, in all the rest of the techniques I'll show you, I'll bring with me all the examples together. I will never try to solve for one example at a time. You cannot do that. Okay, so it seems like we solved the problem. And when we did this, basically, we built a tool that does exactly what I just described. It takes a synthesis problem in Cygos. It reduces it to a verification problem, a reachability problem, and use it at the time we were using Seahorn, and we could verify. And here are some cute things we could prove that came from the paper on minimizing Cygos problems. We could prove that to do the max of 2 numbers, you really do need an if then else. If you do it without if then else, you cannot do it. The max of 3 numbers, you cannot do it with 1 if then else. To do the XOR, you cannot only use and or if you don't have negation. There might be other restrictions here I'm not mentioning, but this is kind of at the high level. If you want to sum 2 numbers and you don't have access to the variable y, you cannot try to do x plus 1, x plus 6, x plus 7. So simple examples that basically came from solving synthesis problems where our goal was to optimize some objective. And this, at the time, was the first of its kind. So we were the first that could do any of this. Existing solvers, when you will ask, can you solve a synthesis problem that has no solution, they will just crash. OK. Now I gave you kind of the obvious technique, which is like, let's reduce to something that we already know how to do, but can we do better? Can we come up with specialized technique for these different problems? So usually, when you start a new problem, this is, again, like advice for new PhD students, don't try to be fancy from the very beginning. Do first something that kind of works, and then you can improve it. But don't start by improving your work. First, do something. And we did the something, and now we understood some problems that were arising, and we were able to address them directly. So I'm going to show you the next technique is, thanks to my colleague Tom Reps, that at the time pointed us to it, is this thing called grammar flow analysis, which is kind of a forgotten gem in the verification community. And so I'm going to resurrect it today for you. So what is the essence of what we are trying to do? Okay, so I'm going to move away from reachability and Seahorn and whatnot. I have a grammar. So this grammar basically can produce programs of the form 1, 2x plus 1, 4x plus 1, and so on. Okay? And really what we are trying to do, if we have 2 examples, in this case, 1 maps to 5, 2 maps to 6, we are trying to reason about the set of possible outputs that every program in this grammar can produce on those inputs. So in this case, if I feed the inputs 1 and 2 simultaneously, I can get the output 1, 1 if I run the program 1, 3, 5 if I run the program 2x plus 1, and so on. Right? That's what I just showed you in the previous slide was kind of doing that. And what I want to do is just check whether my output, in this case 5, 6, the 2 outputs are 5 and 6, is this one of the possible outputs that I can produce? So if I can check that, it means the problem, if 5, 6 is a possible output, the problem is a solution. If 5, 6 is not in that set, the problem does not have a solution. It's unrealizable. Okay? But now we are in a problem that seems like, okay, maybe if I can just come up with the representation of that set, then I can just check this directly. I don't need to encode a crazy verification question. And that was essentially the key idea here. The key idea here is that we can use all the beautiful abstractions that we know from abstract interpretation, and we can come up with new ones to model what this set is. So in this case, very simple one, this set happened to be one that only contains pairs of odd numbers. Okay? I removed the grammar, but you can convince yourself that that's the case. Once you convince yourself that that's the case, if I can prove that indeed that's a valid abstraction, all I need to check is that 5, 6 is not in the set, because 5, 6 is not a pair of odd numbers. Okay, now all I have to do is show you that to convince you that that's indeed the solution. And here comes the beautiful grammar flow analysis. So grammar flow analysis is just data flow analysis applied directly to context-free grammars. And we have a grammar for us, so it seems like a good fit. And this is all it is. I'm going to go slow here and pay careful attention. So I'm going to take my grammar. I just spread it out for what I'm going to do next. This is my grammar from before. And I'm going to just do abstract interpretation on the grammar. So I'm trying to compute the set of outputs that E can produce, that I defined that to be E sharp of 1, 2. And then what are the outputs that X can produce? Well, X is in this case is the input examples. So it's the pair 1, 2. And I'm going to abstract that. Plus, everything is going to be abstracted. And notice that there is a recursive call to E sharp 1, 2. So the definition of this is an equation. This is basically an abstract equation. And now I can solve this by applying my abstraction. So in this case, E sharp 1, 2, I said it's odd, odd. 1, 2, it's odd, even, clearly, because 1 is odd and 2 is even. And everything else is going to be like that. And now if I solve this equation, I get odd, odd equals odd, odd, which means that odd, odd is a valid solution to this equation. And grammar flow analysis just gives you conditions under which this is sound. Basically, it just says, as long as you can find a solution to this equation, your solution is a valid abstraction for that set. And it's actually a little bit better than that, but the clear point here is that I just proved to you that odd, odd is a valid solution there. In particular is what I'm going to call an invariant, it's to get to familiar territory. And once I prove that, I basically solve generalizability. Now, all we needed to do was to come up with these invariants automatically. Okay? And that part I'm not going to show you, but what we showed in this paper, which thanks to kind of rephrasing the whole problem as this grammar flow analysis, we were able to find family of problems for which these invariants can always be computed, and they can actually be exact. And what that means, I'm going to show you in this case, we showed that for SIGOs, where the specification is only given as examples, and the grammar is a subset of linear integer arithmetic, so the examples we had before was 1. For that case, we can always compute exact invariants using grammar flow analysis. And what that meant is that by just moving away from this arbitrary verification problem, we had found a fragment of the problem that was decidable. And this was the first result of its kind. There were actually many papers showing that everything was undecidable about synthesis, and here we have found one case in which it's decidable. And you can read the paper if you're curious about this. That's the PLDI-20. But so this was exciting, because now for the first time, we had realized that this problem was not an arbitrary verification problem, was something we could exploit the structure of. And not only that, besides the nice theory, when we built the tool based on grammar flow analysis, we built a tool that was faster than the previous one on every possible input they could solve, and it could solve new benchmarks. Okay? So things were looking good. In fact, Happing was very happy at this point. In fact, he graduated and he found a job. But so the point, it all started with a problem that had nothing to do with this, which was inverting encoders. So again, story of a successful PhD. I think this is very nice. Like, we started with something and we identified a key problem that people hadn't looked at, and then really it led to a lot of research. Okay. I'm doing well. Good. Time is good. Now I'm going to move to something that is a little bit more esoteric. So brace yourself. Okay. So so far, all I showed you was how to solve problems where we have they felt like simple problems. I think that's probably a lot of you in the audience, like, oh, I think you're telling us you're verifying infinite many programs at once, but your programs are like X, 1, and 2. And that's not that exciting. We want real programs. So to move to actual programs, we needed to handle imperative constructs. Okay, so we want to handle loops, we want to handle all the stuff that people like to reason about in verification. So I'm going to show you now why that is. If what we did before was already pretty hard, what we're going to do now is really, really, really hard. Okay, so the game changes completely. And it took us, so actually this paper I'm presenting, it took us 1.5 years with Jinwoo to come up with sort of the solution I showed you. And we were solving a different problem at first. I mean, before we were solving a different problem, but we spent so much time trying to understand what we were solving that the insight I'm going to show you in the next couple of slides, it took us 2 years to come up with. So now it's going to be obvious, like all things in retrospect. But it was very tricky to move away from the view we had of Cygus. Okay, so the example I showed you before had this form. So what is so special about how we solve this problem? When I wrote the equations that then I turn into grammar flow analysis equations, I use a very important property of Cygus, and that in Cygus, all the programs you generate are expressions. They are not imperative programs. They are not stateful. They are just expressions. So they are x greater than 0. X plus 1. So things that have a type Boolean or int, but they are not state transformers, okay? What that means is that when I write these equations, I know, because of the semantics of expressions, that the value of x is fixed, okay? Variables don't change in expressions, don't change their values. And so I could write these equations as follows. I know that x is always going to be the pair 1, 2. My input is not going to be modified throughout the execution. And clearly, this is not true for imperative programs. So here is a new synthesis problem. So now we have our grammar contains imperative. We're basically trying to find a program of the form nothing or x equals x plus x followed by x equals x plus x followed by x equals x plus x as many times as you want. So clearly, and our goal in this case, I want to show that on the input 1, I want to produce the output 5. This is unrealizable because if we look at the possible values that this can produce, there is only 1, 2, 4, 8, and so on and so forth, right? This program computes powers of 2 in some form, and 5 is not a power of 2. So how do I prove that all those programs, all the programs in the search space are wrong on this input? So how do I prove that this problem is unrealizable? Well, let's try to do what we just did. So I can try to do grammar flow analysis, but now I need to change. So notice before I start that before I had this E of my inputs was the set of outputs, but now I have set S of my input valuation is my set of output valuation. So S says that if I start with x equals 1, I can end with x equals 1, or x equals 2, or x equals 4, okay? So now if I try to define that set, I guess, so the values that I can end up with when I start with x equals 1 is, and now here I have this recursive equation. And the problem is that at that point, x has changed to 2. So to reason about what values x equals 1 can produce, I need to reason about what values x equals 2 can produce, right? Because after I do this first assignment, that x equals x plus x has changed to 2. So that equation is correct. That's the correct definition. But now there is a new variable, x equals 2. So I need to solve for x equals 2. And now there is a new variable, x equals 4. And in particular, this never ends. To solve this grammar flow analysis problem the way I showed you, I will need an infinite set of equations. And we don't like that, because it was already hard enough to solve for finitely many variables. We don't want to try to encode something that has infinitely many variables. So we need to do something else. And again, I'm kind of spoon-feeding the solution here, but at the time, it took us a long time to actually understand what we were doing. And the abstract interpreters in the room will be like, well, you need something relational. Of course, you need to capture the input and output values, not just the inputs. And surprise, surprise, that's what we do. We introduce relations. And so basically, the point is that instead of this S of an input, really what you want to have, you want to have a different relation, let's call it SEM-S, which captures the semantics of any program in S. So in this case, SEM-S of CD holds, the relation holds for C and D, if starting on input x equals C, there is some program that can produce x equals D. And now, if I can compute that relation gives me everything I need. That relation captures the semantic of all programs in my set. Okay? So how do I compute that? So I can try to do it with kind of grammar flow analysis, but really at the time then we realized that that was not going to work very well because it was very hard to come up with relational domains that they were precise enough. Instead, when we were working on these, what was becoming particularly hot, and now it's, I think, very hot, was using constraint-or clauses. And so this is another connection to something that you're all very familiar with. I could actually define what it means for a relation, what it means for a pair to be in that relation. I mean, constraint-or clauses were, I guess, around for a longer time, but here it became very clean to connect them together. Basically, all I'm saying in this implication that you see here is that if I want to model the update S goes to X equals X plus X S, I can do this inductively by saying, well, if C2 can go to C3 in S, so I'm basically modeling this side here, and C2 is equal to C1 plus C1, then C1 can go to C3. So I'm just defining the semantics of that operation inductively. So this is really the semantic of sequence in sequential composition in statements. Okay? So all good. This seems pretty obvious. But now is going to come the problem that was really the actual problem, and that's the one where we got stuck for a long time. And I think that's going to be a bit different from what you're used to. So this example is going to be tricky to follow. So again, a good point to re-wake up if I put you all to sleep. So I'm going to show you a very simple problem, which we have a solution, is OK, we don't know how to do well, and the goal of this keynote today is that you tell me how to solve it. So be all careful, because I know you have the tools that I don't, so I want to make sure you understand the problem. I have this very simple grammar. A contains two statements, x equals x plus 2 and x equals x plus 3. And now I have a loop. The loop repeats one of the two programs in A twice. The semantics here is one of them. It's either x equals x plus 2 twice or x equals x plus 3 twice. So one might think that this relation can be defined as whatever the semantic. So let's go back for a second. The semantics of A, the relation, is every pair of numbers that some program in there can compute. So 0, 2 can be computed by x equals x plus 2, 0, 3 with x equals x plus 3, 1, 3, and so forth. When I take their product, like I do there, which is what you will do in a compositional technique if you only had one body of the loop, I'm in trouble. Because in the product, I also consider the case in which I interleave what loop body I have at each iteration. So in particular, this allows to do x equals x plus 2 followed by x equals x plus 3. So this for unrealizability is sound, but massively imprecise. I'm basically looking for an invariant that only uses program variables, but that is true for an infinite number of programs over those variables. And that's going to be very, very hard to find. Okay, so this is a key point. We call it the shifting sense problem. So tell your friends about the shifting sense problem. But seriously, we don't know how to solve this well. We have a solution, and we have a theoretical solution as well. But this is the key essence of the challenge of proving unrealizability, is that you need to remember what program was run, not just what behavior it produced. And the solution in this particular paper was that then, instead of having the relation just talking about inputs and outputs, we needed the relations to remember what program you were actually running. So in this case, we are not building just a relation that says this input can lead to this output, but really we are basically effectively building a full program semantics of the form. The input gamma, when fed to the input to the program TS, produces gamma 1. And now, how do we define this relation? Well, the good news is that there is a whole community called PL community that writes things like this. And basically, it's literally just operational semantics. In fact, we got so excited about this that we built a whole format for describing this. And that's a different talk if you want to look at. But it's called SemGus, which is basically SciGus++. But long story short, you have now a way to describe. Essentially, what I'm describing with this relation is, in this case, the bottom says gamma on while TB do TS produces gamma 2 if gamma TB produces the value V, and so on. And now you can write constraint-or clauses to describe all of these relations. So that's just a constraint-or clause. But if you look on a PL textbook, it just looks like a different notation. OK. So once we saw this, we were basically back connected to something that the SAS community knew how to solve, which was verification problems. And in particular, we started with something that looks like this. So I have a grammar of imperative programs. So in this case, a grammar of a bunch of things that can loop. And I have their semantics given as constrainer clauses. And these I can write it manually, or it can be extracted automatically from most programming languages. And then I have some examples. In this case, I want that on input 6, 9, the output of the first x is 15. And this is just an example that shows I want to compute the XOR of those two numbers, the bitwise XOR. And if you remember before, I kind of told you the XOR cannot be computed using just AND and OR. And in fact, none of the programs in here on this input can set x to 15. Okay? This is going to be important in a second. And now, to solve this problem, to solve this unrealizability question, because I have everything set up as CHCs, all I had to do was one step. I had to write one last CHC, one last constrainer clause. I'm not going to show you how, but you can also encode the syntactic structure of a grammar using constrainer clauses. So you can inductively define what programs are in the grammar by just following the rules of the grammar. So this says, can you give me a program T in this grammar such that if I run T on input 6, 9, I get 15 something. And the semantics relation star, remember, is defined by those semantic relations we defined before. So the cool thing is that the top part, you only need to do it once for each language you want to do unrealizability for or verification for. And then at the end, you're just going to ask queries of the following form. So we are back to a normal verification question. It's like, can you give me a program T that is correct on the inputs? Well, if you can do that, you have proven that T is a solution. So if you can prove in constrainer clauses that this result is reachable, solution T, you have found the solution to the synthesis problem. Dually, if your solver can show me that this query is false, it cannot be proven, you have proven unrealizability. And it turns out that existing solvers, in particular Spacer, are much better at proving that there is no program than proving that there is a program. And that's what we did. We built a tool that essentially will take a grammar of imperative programs and examples, and it will spit out a CHC query over a bunch of CHCs, and then it will use the tool Spacer to check whether the query was possible, had the solution. And here, we had a bunch of simple, small examples, but I want to show you just some cute ones, that these are things that, again, like, you know they are true, but if you think about how to build a proof, it's a bit tricky. So we could prove that you cannot swap two variables if you don't have an auxiliary variable and you don't have XOR or a plus. So you cannot swap two variables x and y if you don't have some either additional storage or expressive power in the language. And you cannot do the XOR, the example I showed you of two bit vectors, if you only have AND OR. Even if you have infinitely many possible loop body or whatever, it doesn't matter, because you're never going to be able to build what you need. And we built a benchmark suite, and we could solve about half of it. And but yeah, essentially we were able to, for the first time, to prove that something about infinitely many imperative programs. So these are complex programs. Okay. So if you were asleep again, this is another exciting part to wake up, because now we go into the grand finale of this thing. Okay, perfect. So remember, this thing is basically, I cannot do the XOR of two variables unless with only AND and OR. And when we fed this to a CHC solver, the way it proved, actually, that this was not possible, it wasn't, that part wasn't the important part. What it was interesting is that it came up with this invariant. And this is an invariant that I promise you, you've never seen in your, well, maybe you've seen, I don't know. But most likely you haven't seen an invariant like this before. So this is an invariant that says, you don't need to read fully, but basically it says, all the programs in this set the third bit of x to 1. So you've seen a lot of invariants of the form, the third bit is always 1. But this is different. This one says, every program in this set is an invariant that is true for infinitely many programs. An invariant specifically tells you this invariant is true for infinitely many programs. Okay? It's different than a loop invariant, which is something that just says true. This one says, no matter what program you write, this is true. And once we saw this, again, story of a successful PhD, this led to the next paper. We were like, wait a second. That's what we were missing. We were looking for invariants about inputs and outputs, But what we really need to do is to look for invariants about sets of programs. So the invariant cannot only talk about the relation that the problem specifies, the invariant needs to talk about what program is building that relation. And that's what I need help from this community, and that's going to be what I'm going to end with. But like, how do we build such invariants? We don't have abstract domains for talking about sets of programs. Or with the ones we have, they're not quite there yet. And so really, this was the problem. Unrealizability, and in general, these verification problems, to solve them fully, you need to build invariants about infinite sets of programs. And this Jim would then write this paper, which I think I love it personally, is basically he came up with a logic, like Hoare logic, for talking about sets of programs. And so this is what normal Hoare logic looks like. So you want to show that if I start in P and I run S, I end up in some subset of Q. Our new logic lifts these to sets of programs, and we call it unrealizability logic. That was a faux pas. We should have called it infinitely many Hoare logic or something, I don't know. Because it doesn't have anything special to unrealizability. It actually can be used for reasoning about any problem of this form. But basically it says, if I start in P and I run S1, I get here. If I start in P and I run with S2, I get here. If I start in P and I run in S3. So if I pick all those programs and I get some sets, the triple is true if any of those programs ends up in a subset of Q. Okay? So it looks like we can reduce everything by doing, it looks like we can solve the thing on the left with the thing on the right with the thing on the left, but we cannot, because if you understood everything I said in this talk, just reasoning about inputs and outputs is not going to be enough. We really need to remember which program produces what. So that's kind of the key part here. I'm going to be very brief on this part of the talk. But if you really want to be able to have a complete logic for reasoning about this problem, you cannot just do things of the form P as Q. You really need to talk about, your logic needs to capture what happens within the set S. Okay? And so if you read the paper, there is a lot more on this. But that's really the challenge. But I'm going to show you, and why does this tie to unrealizability? So in normal program verification, you use Hoare logic to say PS not bad means that nothing bad can happen. If you want to prove unrealizability with the logic on the right, what you're going to show is that all these programs cannot satisfy the specification. Okay? Okay. So I'm going to still draw some analogy with normal Hoare logic so that we kind of are in a good place here. But if you want to prove something like, one nice property of Hoare logic is compositionality. If you can prove things about individual programs, when you put them together, you prove things about composed programs. Okay? So that's captured by rules like the rule for sequencing that says, if you can prove that S1 goes from P to Q and S2 goes from Q to R, then S1, S2 goes from P to R. Okay? And we have a similar rule in our logic, but notice that this is now a little weird. If you can prove something about a set of programs and something about another set of programs, their composition is the Cartesian product of all those programs. So I can take any of the programs in the two sets and run them in any order. Okay? And that's what our rule captures. So notice like I run x1, x1, x1 by2, and so on. So we get this nice property again that because of the definition of the problem, we get compositionality. So I'm going to show you an example. I'm not going to show you the rules of the logic because it's pretty complicated, but I'm going to show you some of the insights. And in particular, the key insight is this invariance about infinitely many programs. So how do I prove? I'm going to show the example with the non-imperative statement, something like just expressions. But we know that invariant from before, that if I start with x equal 1 and y equal 3, I always get an odd number. How do I prove this? That this grammar always produces an odd number with x equal 1 and y equal 3. So the idea, this is the triple I want to prove. I want to prove that if x is equal to 1 and y is equal to 3, the output, I'm going to call it VE, the output that I produce is odd. To prove this, I'm going to have to prove that this is an invariant of my search space. This is an invariant of all the programs in the search space. And the way you do it is basically, I'm going to have to prove it by assuming that this is true. So this is similar to relational summaries in procedural verification. So to prove that something is true for a recursive program, I have to assume it at each recursive call and then prove it for the main program. And here is the same idea. To prove that that is true, I have to prove that assuming that hypothesis, I can prove that it's true for every possible production in the grammar. So in this case, assuming that this is true, can I prove that it's true for X? Assuming that this is true, can I prove that it's true for Y? Assuming that this is true, can I prove that it's true for E and E? So the case for X is, I'm going to use I and O as shorthands for the premise and postcondition. So let's start with this one. This one is very easy. So for X, how do I prove that starting with X equal 1, I get an odd number? Well, X is already 1, so the output is 1. And with a weakening, I can show that the output is always odd. And similarly, I can do it for Y. So this is just, right now it looks like normal Hoare logic. Now the interesting stuff happens here with the recursion. How do I prove this? So now I'm using my inductive hypothesis. In particular here, the premise is the same as what I'm trying to prove. So E satisfies this invariant because I'm assuming that E satisfies this invariant for both of the sides of E. And now, basically by induction, I'm doing a proof by induction. Now, how do I prove that E and E satisfy the invariant? Well, that's just the semantics of N. If I take two odd numbers and I take their AND, their bitwise AND, I get an odd number. So really the key point here, if you want to remember anything, is that the logic contains these invariants where the center E is not one program, is a set of programs. Okay? E is the set of all programs derivable from E. And the logic allows you to do proofs by induction over the syntactic structure of the grammar. And if you can do this, in this case, you basically establish that this is indeed an invariant. And with everything you saw in the talk, this means that the problem is unrealizable. I cannot show you everything, unfortunately, so there is too much to cover. But the logic is much more complicated because it has to capture all the issues that I highlight in this talk. In particular, remember we said you need to run all the inputs at once for unrealizability, otherwise nothing works. So the input is not going to be an input anymore in the sense of a variable. It's going to be a vector of inputs that I'm going to thread to my program. And some proofs, if you want completeness, require the vector to be infinite. For loops is a mess. We don't have a good compositional rule for loop. We have a rule that is sound and complete. So the rule in the paper, actually, we just found a bug in it. So coming soon in the next week, there is going to be an errata published. But we fixed it. It's a small fix. But it's very tricky to do it for loops because of what I showed you before, where the loop body can change. But assuming with this fix, we have the first logic that is sound and relatively complete in the sense of our logic. And we also, the cool thing is that this logic actually subsumes everything I showed you in the talk. Like every technique we showed you, we can now translate it as finding invariants in this logic. Like the logic is a complete proof system for everything I talked about so far. I'm going to show you this cute example. This is an example where to build a proof that all the programs are wrong, you need infinitely many inputs. And it's super simple. I'm trying to come up with a program that computes the identity function. But all my programs are of the form if x equal a constant returns a constant, with as many if then else's if you want. So this example is cute because no matter how many inputs you give me, I can just put enough if then else's to make it correct. I can choose if x is equal to 1, return 1, if x is equal to 2, return 2. But no matter how many you give me, I can find the witness. But to prove that this is actually unrealizable, you need something like this esoteric invariant over infinite vectors. So if you have a good solver over infinite arrays, so we're using Vampire now, but if you have a better one, or you think you can reason about invariance of that form, please come and talk to me because we need such a good solver. Okay, just to end real quick, I talk all the time about unrealizability, but I want to get you excited because I assume that none of you cares about unrealizability. I probably am the only person in the world that cares about, but actually it's a very important problem, and I'll show you why it's an important problem. So here is another problem where such a logic or such a system could be helpful. So this is a paper from FSC 18. So what they were solving here is that they have a program, and some piece of the program is missing. Actually, they are trying to come up with that piece of the program. Oopsie. OK. They're trying to come up with that piece of the program. So there is I'll tell you the story. We improvise. No, everything is same signal. Oh, that's a good question. That could be the problem. Oh, I ran out of battery. Oh, that was my fault. OK, we'll finish improvisation. OK, so the point I'm trying to show here is that I'm trying to find a program that is correct. I'm trying to find the missing piece of the program, and I cannot do that. So to do that, that paper uses symbolic execution over a program that is missing a piece. And when you do that, basically, they get too many symbolic execution paths. So all the paths, you get exponentially many paths like in normal symbolic execution, and they want to prune away the ones that are infeasible. And pruning those paths away is a form of what we are just doing. You want to show that no matter what program you put in the hole, the paths are not possible. The next application I was going to show you is, and that's the dream that started this whole project, is can we do CDCL for program synthesis? So if you want to do CDCL for SAT solving, what you build is proofs that some subset of the space you've explored is not leading anywhere. And we don't know how to do that for synthesis. So in synthesis, you're searching for a space of programs, and now at some point, you get like, oh, I'm in a place where I'm stuck. This is leading nowhere. So we know sometimes how to realize that we are stuck, but we don't know how to learn why we got stuck. And the invariants I showed you earlier, they give us a hope that we can build these proofs that maybe are reusable of why I got stuck. Okay? So in the same way in which CDCL can create blocking clauses, can we create blocking synthesis clauses through these invariants? And the last application is if I get my code from an untrusted source. So in JavaScript, you can have this eval statement that basically takes a string of code and just runs it. And I know this community has written papers about how to reason about that type of code, but in general, it's very hard because the code comes as a string, and I need to reason about what it does. So I can either non-deterministically assume it does something, but I can try to reason about it explicitly to a logic like this. In particular, if I know the grammar that code can come in, maybe I have some restricted language that code can come in, this logic allows you to talk about that. Okay? So unfortunately, that's my fault. I forgot to plug in the computer, so I paid the price. But that was the end of the talk. The last thing, basically, I wanted to leave you with, I have a logic that allows me to reason about unrealizability. And this logic allows me to talk about infinite set of programs. And the things I was going to ask for your help with is, how do we build invariants for sets of programs? And for those, we will need good support for infinite vectors, for abstract data types, because we can use data types to model programs. And that's it. Thank you.
So thank you very much. It was fascinating. So questions?
Hello.
Yes.
So this is very interesting, and I think it's oddly connected with type systems, in the sense that you are saying for all the programs that follow a certain grammar, then certain properties of the invariant hold. Mm-hmm. A type system said for all programs that are well typed in this specific type system, that it can be an extra layer of type system over others, then certain properties hold. So have you thought about the relation between this extended hold logic and the whole area of type systems?
Yeah, so that's a great question. The question is basically like, oh, this sounds a lot like type systems. So there is first the easy answer, which is type systems and verification a la Hoare logic. They are all very connected indeed to start with. Like in general, well, one is targets different type of programs. The other one, but in general, you can translate the inductive principle of how you do verification together. Now, how to map it to these sets of programs? So it's true that one type system that you specifically design allows you. It's a bit different now because you design it for a set of programs, but they produce proofs for one program, typically. Like when you give me a type in derivation, it's decoration of one program.
Yes and no. Like,
okay.
The grammar is the type, like, instead of being restricted to, thank you.
Okay.
In a type system, instead of being restricted to a simple BNF grammar for the program that will have to respect this property, you have a much more complicated criterion that is the existence of the type proof. Mm-hmm. But then, in the same way, you say for all programs that verify this grammar, properties hold. A type system says for all the programs that verify this type system, those properties hold. So we just have a richer constraint, mm-hmm. where instead of just being a grammar, it's a more complicated but still usually inductively defined logical restriction.
So I think it is in principle possible to come up with something that decorates the grammar itself. And in a way, that's what we did. Yeah, the question is, can you reframe it as a type system? And I think the answer in general, there is a lot of connections in general with how we do verification in the abstract world or in the abstract interpretation world or logic and type system. So I think the same connection should be established here. Yeah, and I'm looking forward to somebody doing that. Yeah, thank you.
Yeah, thanks for the nice talk, Loris.
Yeah.
This is more of a check of my understanding of intuitions, but it seems like the shifting sands problem is very similar or related to kind of like the program alignment problem where you're doing differential analysis or relational Hoare logic or something.
Yeah.
Can you
So
elaborate?
that's a great point. So if you only have finitely many programs, then in fact in our logic you can do something easier, which is basically you can take the case analysis of those. The alignment in the tradition, like the issue is that program alignment works really well when programs align. So most of the techniques are kind of assume that because the program is itself the same most of the time, then the alignment is somewhat easy. In our case, the programs are completely different. And so, but you can have a program that is a loop in the search space and a program that has something completely different. And so we don't know how to do the alignment in a way that is meaningful. That's kind of the issue.
Right. So like exactly like when you're doing differential analysis, you typically assume it's the same program or structurally very similar, and that's where you can get proofs. But exactly when they're semantically the same but syntactically different, that becomes hard. So is that
exactly? Yeah. So we don't know. That's exactly where right now we don't know how to build proofs efficiently when the alignment doesn't happen.
Got it.
So we need to rely on a constraint solver to tell us, oh, we can do something.
Okay, Katrina?
Okay, thanks. So when you talk about invariance of sets of programs, another connection that comes to mind is, well, what some people call hyperproperties. Have you?
Yeah, so actually that's a great point. And the reason it took us years to also do a lot of these things, because we asked the same questions you're asking, and every time we thought that was the solution, and then we realized that we were looking at the program wrong. And I think these are all things that essentially everything you're saying, it can be put on top of this reasoning. So the hyperproperties part is like, how do I prove unrealizability in the sense like, how do I prove that all the programs in my search space are non-commutative? Now you need hyper reasoning on top of this. But hyper reasoning doesn't give you this by itself, because you still need to remember which program was running. But you're very much right.
Yeah, but when you reason about sets of programs, the invariants are talking about properties of these sets of programs. So in a sense, when you have and some analysis that can do hyperproperty reasoning, maybe you can use it to find invariants about some of these kind of problems.
I think potentially, I think you might be right. Potentially, to some extent, you can find it. If there is finitely many, I have to think about the specific analysis you have in mind. But yeah.
I don't have any analysis in mind. I'm saying, and hypothetically, hyperproperty analysis that could find invariants maybe can help with solving some of these problems.
That's true. Generally, I think these two words are very connected, the sensitivity analysis and the hyperproperty. And I think a lot of it comes down to subsets for which you can find alignments. And if you have one program, these things are always possible-ish. Like the issue for us is like, even if you take the simplest grammar, they all look very different. I'm back connected if you want. Yeah, perfect. So.
Okay, so I have one question related to the first and the last one, and then I will give a parole to Andy. So do you have abstract domains that come to your mind to abstract a set of programs?
Yeah, so that's essentially the part that I'm struggling with. And first, thanks for everyone who paid this work. But that was my last slide. Essentially, this thing on data types, that's the question. So right now we are relying on Spacer, for example, for the third work I presented. And Spacer somehow can build internal invariants about data types. And they have various weird representations. But there is really no good work on saying, here is a set of programs for which something holds. So we need something about good abstraction for data types. I know people have looked at this in the world of shape analysis back then. There was one way. I mean, data structures were effectively kind of similar reason. We really need to reason about trees in some form. But I think this really requires a fundamental rethinking of, we need some relational domain that effectively decorates trees with their meaning. So something that is like trees of semantic triples of their domains. And so this requires to design new domains. And I don't know what to do in this case for the sets of programs. Like we have some very simple things like, oh, you can get prefix abstractions. Every program that starts with this prefix, this proof is going to hold. And that's what you're going to get for the CDCL example I gave, where basically any program that I can complete from this partial program is going to fail because of this reason. In particular, on the input 5, is going to output a number greater than 6. So that's an invariant, and now if I can build a lot of those in a very nice form, maybe I can do something smart. Yeah.
Thank you. Andy?
There's also a question here.
After? Oh, okay.
Yes.
Yeah, so I found the idea of grammar flow analysis to be particularly intriguing, and specifically when thinking about SIGUS in general, because you have these choices of, do I fill out this part of the candidate program that I'm synthesizing, or the other part? And so I was wondering if you had looked into using this abstraction to automatically prune search space while you're doing SIGUS.
Yeah, so that's actually, there was another application that I had when my computer died, but that's a great point. It's like, if we can compute the abstractions, the issue, there is this issue with profitability with synthesis, that pruning is only good if it prunes more programs, if the time it takes you to prune is less than how much time it will take you to explore a good chunk of the program in the space. So if the invariants are too expensive to prune, that's not a good idea. But we have techniques that some of the solvers that we are building do that. They prune based on these ideas. There was actually a follow-up paper from our second paper, the grammar flow analysis paper, that they built a simple pruning strategy based on abstractions. They didn't frame it as grammar flow analysis, but effectively they had a very cheap abstract domain that whenever possible it would prune, and it was very effective in practice because it was very, very cheap. So it's like, very rarely something was unrealizable in the subpath, but when it was, you could throw it away in a way. So it's a great idea, yeah.
So I guess as a follow-up question, how much of this program logic are you able to automate through like abstract interpretation, and how much of it is manual?
Future work.
Fair enough.
I have a student now that is basically working on that. How do we automate it? And he has built automation, so we can do simple proofs. But invariant checking is extremely hard, infinite vectors and whatnot. Invariant generation, we have no idea. So we can use SIGUS to generate trivial invariants, but anything complicated that involves quantifiers like the one I showed at the end with the for all, then we don't know. But yeah, I would love, if anybody has ideas, yeah, I would love to hear those.
Okay. Andy?
I think the intuition behind the first question is correct. I'm sorry, my brain works slowly these days, but there was a best paper in Lobster about 2 or 3 years ago, and it was a PhD student who used the Curry-Howard isomorphism to constrain the space of synthesizable programs, and he used that to improve the synthesis process. So that might be worth looking there.
I think I'm familiar with the word. So in general, in the synthesis word, there are many words, but one of them is sort of type-directed word, and you're very much right. Typically, they don't look at grammars, I believe. Like the one, maybe the particular paper you have in mind is something different, but usually they look at, so usually you have a typing judgment and you're trying to do typing habitation and trying to find the term, a program that has the proper type, and the type is the specification. And now you can explore using type-directed synthesis. You can use the rules of your type system to explore the possible derivations. And then at some point you will get you get a local proof that there is no inhabitant for the local problem you've solved. So I'm saying it's very similar in principle. The challenge here is the grammar restriction. And sorry if I didn't make that clear enough. Like, there are many synthesis formulations out there, many of which are always solvable in particular, because if you ask me, is there a program that does something and you don't restrict the search space, then the answer is yes, unless the problem is undecidable. And typically in type-directed synthesis, they look at search spaces where there is a nice type system you can design. Once you restrict the search space, and that's what we, maybe I should clarify, what we tackle today is not the synthesis as in second order quantification in logic, where you say, is there any term that does the thing? I'm asking, is there a term in this very constrained syntactic search space that does the thing? So that's really what breaks inductivity and makes it very, very hard to do reasoning. Yeah.
I'm sorry, we are already late, but you can ask offline.
I'm around, yeah.
So thank you very much for your talk and your answers. And we are going to go to the next talk. Yes, please applaud.